Hi, my name is Mark Turcotte. I'm a visiting professor in the mathematics department at the University of Texas in Arlington, Texas, in the United States. 我是马克教授，在 UT Arlington 大学，在美国的德州。Today I will explain to you how chemical reaction rates depend on temperature. So we're going to consider a binary reaction where two reactants, A plus B, producing a product P at a forward rate K sub F. So the rate of the reaction is the time d dt time rate of change of the concentration of products. That makes intuitive sense. This expression is a measure of the speed of the formation of products. So dP, the concentration of P over dt, is equal to Kf, the forward rate of the reaction, times the concentration of A times the concentration of B. So, and the units of Kf are 1 over molar second, by the way. So the issue here is, what is the dependence of the rate of the reaction? That is, what is the dependence of this expression, d concentration of P dt, on temperature? Well, we can look at the right side of the equation and ask ourselves, where could temperature dependence be? Obviously, it can be in Kf, but could it be in the concentrations? I don't think so, because the concentration of X is equal to the number of X divided by the volume. So that cannot depend on temperature. Therefore, the entire dependency on temperature is on Kf. It turns out that there is this famous equation dating back from the last century called the Van 't Hoff equation. And it reads like this: the temperature, dt, of logarithm of the equilibrium constant, K, is equal to delta H naught, the enthalpy of the reaction, times K over Boltzmann constant T squared. So there are some quantities that need to be defined. This is a plot of energy versus a reaction progression measure of a reaction variable called psi, which we can imagine for the purpose of this demonstration as being the progression or time, essentially, as the reaction progresses. So, so how does the energy go? Well, it starts out in the reactants, and then it increases to a maximum, and then falls below the initial level. This amount of energy is what we call over here delta H naught, the enthalpy of the reaction. The difference between the reactants energy and the maximum of the curve is called EA, the activation energy. And this is the transition state energy. And on the other side, the difference between the top of the hump and the products is called EA prime. So the idea is that molecules of reactants have to pass a barrier. And the barrier, the height of the barrier that they have to pass is EA, E sub A, the activation energy. such that the reaction progresses from reactants to products. Obviously, because the energy of the products is lower than the energy of the reactants, then the reaction progresses this way. I mean, molecules of reactants turn into molecules of product. So this is the Van 't Hoff equation, d log k is equal to delta H naught over kt squared. So there's a famous Swedish physicist who lived from 1859 to 1927 by the name of Arrhenius, A-R-R-H-E-N-I-U-S. And he made the following assumption, that T, the temperature of ln Kf, the forward rate, this is different, is equal to Ea, the activation energy, divided by the Boltzmann constant times T squared. And based on this assumption, based on the Van 't Hoff equation, Arrhenius derived an equation for the forward rate of the reaction, which you can integrate. You can integrate this with respect to temperature, and it's pretty simple, so I won't do the details. So Kf is equal to A e to the minus Ea over Boltzmann constant times T, the temperature. This is called the Arrhenius derived equation. This is the Arrhenius equation. This is the Boltzmann equation. So, what matters in the reaction is obviously those molecules that can go across the hump, that have enough energy to go above the hill. It is not the mean energy of all the molecules in the system. It is how many molecules that have enough energy to pass the barrier. So it turns out, and I'm going to erase this side here, but just leave the Boltzmann equation. It turns out that if you plot the probability density as a function of energy for two temperatures, T low and T high. At T low, the curve looks like this. At T high, the curve looks like that. And this is maybe the mean energy at T low. And this is maybe the mean energy at T high. So notice that the mean energy goes up as you increase the temperature. But it's not the mean energy that matters. It is the number of molecules that have an energy greater than Ea. So the number of molecules is given by the integral under the curve. So the question is, when you raise, this is T high, and this is T low. So what happens is, the question is, when you raise the temperature from T low to T high, how many more molecules are above threshold? Well, it's pretty clear that the number of molecules, that additional number of molecules above threshold is given by this, which is basically the difference between the integral under the first curve over here and the one over here. So these molecules pass threshold. So raising the temperature obviously increases Kf, and it increases it in relation to the number of molecules, additional number of molecules that pass the threshold, which is basically given by the difference between the two curves. So this shaded area. But to be more specific, you can compute the effect as Kf T high over Kf T low, taking the Boltzmann equation, A minus E sub A divided by K Boltzmann constant T high over A e to minus Ea K T low. So Kf T high over kf T low is equal to A cancels out, e to the minus e A over k Boltzmann divided by multiplied by 1 over T high minus 1 over T low. You just bring this term up over here. So that gives you, essentially, it tells you what happens when you raise the temperature. So when T is increased, then Kf is increased. So, and then because dP dt is equal to K forward times A times B, concentration of A and B, then when Kf is increased, then dP dt goes up. So the rate of the reaction goes up. And then obviously when the concentration of A is, I guess the question was what happens when it decreases. Well, if you decrease the concentration of A, what does it do to the rate of the reaction? The rate of the reaction is the rate of formation of product. So obviously it decreases it. You make this smaller, then this goes up. So the effect on temperature is in Kf, the forward rate, and the effect on concentrations is on A and B multiplied together. Remember, we're interested in what happens to the time rate of change of the formation of product, dP, the concentration of P dt. Thank you. 谢谢。